Hi there again. So here we are again. Try it for in triangles. So one angle of a right triangle measures 56 degrees. What is the measure of the other angle? Oh no. Hey, wait, no, we know two angles, right? Right triangle, right there. I hope that records. So we know that is 90 degrees. So we know that 90 plus 56 has to add up to 180 degrees. So what's 90 plus 56? 146. So 180 minus 146 is 34. Very simple. This is we're just going to move through this real quickly. Um, Here's another one, example 5, where they want us to make an equation. So the measure of one angle of a right triangle is 20 more than the measure of the smallest angle. So we know that one of our angles, right triangle, is 90. So let's say, so we know one is 90. Let's call the other one A, and then we know another one is 20 more than A, so A plus 20. So we have A plus 20 plus 90 has to equal 180. So when we algebraically manipulate this, we end up with 2A plus 110 equals 180. Let's solve for A, so subtract 110 from each side. 2A equals 70. So A is 35, the first angle, means the second angle, which is 20 more than that, is 55 degrees. And the third angle was a given at 90. Let's do the check. Do they add up to 180? They do. So huzzah. Okay, try it 5. I'm just going to talk through this. Measure of one angle of a right triangle, boom, 90 degrees, is 50 degrees more than the measure of the smallest angle. Find the measures of all three angles. Wow. All right, so we know that 50, well, one is 50 more, so let's call the smallest angle A. Then we know the next one is 50 more than that, so then we have another angle called 50 plus A. And our last angle is 90. So the three of them done up should add up to 180. So we know that A plus 50 plus 90 equals 180. So that's 2A plus 140 equals 180. Subtract 140 from each side, and we end up with 2A equals 40, which makes A 20. So our smallest angle is 20. Our next angle is 70. And we know that we have a right angle in there. So 20 degrees, 70 degrees, 90 degrees. So now similar triangles. And this is the guts of geometry, triangle geometry. Will lead us into sine, cosine, tangent, and we will do a few proofs when necessary to illustrate things to you. So we have similar triangles. So when we use a map to plan a trip, a sketch to build a bookcase, or a pattern to sew a dress, we are working with similar figures. In geometry, if two figures have exactly the same shape but different sizes, we say they are similar figures. One is a scale model of the other. And there you go. Think if it's a similar triangle, it's basically they're different at the same triangle at different scales. Remember that. The corresponding sides of the two figures have the same ratio, and all their corresponding angles have the same measures. So, similar triangles, the lengths of your sides are going to vary, but your angles will all be the same. And we have rules, which I'm sure we'll get into some of them, about some hard and fast rules that we can use in proofs to prove that angles are similar. Um, so, we'll look at figure 7 here. Um, I just need to see how much time I have left. I have 10 minutes, so let's set a timer for 10 minutes because I don't want to get cut off. Come on. Why am I having so much trouble with this today? There we go. All right, sorry about that. So let's go back to our... So we know we have a side b equals 12. I better still be recording. Good. 12, 16, and 20. So we have a smaller triangle, x, y, z, 3, 4, 5. So we look at the ratios, 16 over 4, so that side to that side, 12 over 3, 20 to 5, they're all a ratio of 4. So they are similar triangles. So properties of similar triangles. If they are similar, their corresponding angle measures are equal, and their corresponding side lengths are in the same ratio. So a over x equals b over y equals c over z. And we will do many examples of these as we go through, especially sine, cosine, tangent. The length of a side of a triangle can be referred to by its endpoints, the two vertices of the triangle. For example, in triangle ABC, the length A can be written as BC, the length B can be written as AC, and C can be written as AB. And we'll use this a lot, especially when we get into the calculations. I will start using that notation. So here they said A, so we can say the line or the side BC is A. So we got the figure provided. So let A equal the length of the third side of triangle ABC. Let Y equal the length of triangle XYZ. So the triangles are similar because we're told they're similar, so the same ratio. So figure out the ratio of two that we know. See, we don't know what the ratio is of to y yet because we're looking for that, and either A because they're unknowns. But the two we do know, that 4 and 3. So our ratio is 4 to 3. Or you can write it as 3 to 4. Right? Yeah. Because you're dealing with similar. It's just this one's bigger, this one's smaller. But for the purpose here, let's say the ratio is 4/3. So the ratio of AB over XY is 4 over 3. So the ratio 4/3. And then we know from the previous blurb that the ratios of the other side should be the same. So let's see, which one do they want us to find first? Let's find A. So we know our ratio is 4/3. Okay, so this one has to be larger. A has to be larger than 4.5 by a ratio of 4/3. So we would do 4/3 times 4.5. You want to do that for me? Can be my designated calculator, or I can do it here too. So 4 over 3 times 4.5, and I get 6, basically. So we know that A should be equal to 6. So we got that. And then B, to solve for Y needs to be 4/3 less than 3.2. So the fun part with that is we can just multiply by the reciprocal of 4/3. So that's 3/4. So let's do 3.2 times 0.75, which is 3/4. And we get 2.4. Is that correct? Yep. And y is 2.4. So we've measured a fraction as a ratio, and then we've done what we've been doing all course, working with fractions. And so Sometimes you divide by the fraction, sometimes you multiply by the fraction. But if we're dividing by a certain fraction, it's the same as multiplying by the reciprocal of the fraction. So that's what we've done here. You know those operations. So try at 6, angle ABC is equal or is similar to triangle XYZ. Find A. All right, let's find a ratio here. All right, what do we know on both sides? We know 17 to 25.5. So let's calculate what the ratio is. Those are the hypotenuse. Are they hypoteni? I don't know. I don't think so. So let's do 25.5 divided by 17. We end up with 1.5. So triangle XYZ is 1.5 times, its sides are 1.5 times larger than our triangle ABC. So that means that side A times 1.5 is going to give 12. So we can say 1.5A equals 12. So when we do that, 1.5A equals 12. Now we got to get that A all by itself. So let's divide each side by 1.5. What's 12 divided by 1.5? Where's my little handy dandy thing? 8. So A equals 8. And since we're here, let's find Y. Same thing. So with our ratio of 1.5, we know that Y divided by 1.5 is 15. So Y divided by 1.5 equals 15. So let's get rid of that 1.5. We multiply both sides by 1.5. We end up with Y equals, I believe that would be 22.5. Yeah, so we end up with 22.5 as Y. So we did it the same way. So, and then just some nomenclature on right triangles. You heard me say, we have 2 legs and a hypotenuse. The hypotenuse is the angle opposite the right angle. So you can see whatever orientation we have our right triangle, the hypotenuse is opposite that right angle. The right angle, yeah, none of the side, yeah, just that's what we remember. So we're going to stop here, and now we're going to talk about the Pythagorean theorem here in a moment. So I will pause this recording, and there